Hello guys, how are you?
Hey teacher, fine, and you?
Fine, thank you.
Hello, teacher.
Hello. We will wait a couple of minutes and then we will begin the class, okay? To see if somebody else logs in.
Teacher, I have a question.
Yes, hello.
When is the final exam going to be?
No, I sent you an email, an announcement just a couple of seconds ago. It will be Monday, 4th of December at 8.
Okay, thank you.
You're welcome.
Teacher, where will we present the exam?
We don't know yet. I will let you know as soon as I know.
Okay.
Okay, guys. Well, we are going to start the class. A couple of things before we begin. The final exam will it doesn't change the dates. Okay, so we are not going to have a departmental exam. We're going to have an exam with me and an exam with each professor. Okay, so our exam is going to be on Monday, the 4th of December at 8 a.m. Okay, you have an announcement in your email right now that says the same thing. We don't know the place just yet. Okay, so as soon as I know, I will let you know. They changed the schedule for each exam, so you can if you have two exams in the same day, that you can be in the two exams. So they are giving 1 hour of space between each exam, so you can be there. Okay, so don't worry for that. So that our exam is going to be the 4th of November, Monday at 8 a.m. Okay, and that's it. Okay, today we're going to solve the homework.
Profe, antes de que comience una pregunta, perdón.
Sí.
Entonces, el examen final lo va a hacer usted, no es departamental.
No, bueno, no es departamental, pero cada examen está aprobado por los otros 3 profesores de balance de materia.
Ok, sí,
Hasta
está bien.
cierto
Gracias.
punto es departamental, justo en el sentido de que el nivel, pues, lo acordamos entre todos, ¿no? O sea, yo no, digamos, ningún maestro hará su examen unilateralmente y pone lo que se le dé la gana y tantar, ¿no? O sea, el chiste es que ponen una propuesta y los demás profesores dirán, bueno, pues oye, pero el nivel está muy bajo, muy alto, o lo que sea, ¿no?
Ok, sí, está bien. Gracias.
Vale. Bueno, entonces, eso. Okay, so today we're going to solve the air conditioning homework. And then if we have time, we're going to start talking about transition balances, okay? But they depend on time, okay? So let me share the screen so you will see exactly the same thing as me. So this was the first problem, right? This one is just was the use of the the psychometric chart. Okay, so we have to begin with the points that we have, with the information that we have. The information that we have in this problem is that we have a room at 1 atmosphere, 35 Celsius. If the problem or the information doesn't say what kind of temperature it is, if it's a wet bulb temperature or it's a dry bulb temperature, you have to assume that it's a dry bulb temperature. Okay, you can't say that it's the wet bulb. And then it says that the relative humidity is 40%, right? Okay, so we have two different points for the diagram, and with those 2 points we can obtain everything else, right? Okay, so if you read here in the diagram, you see in the x-axis you have dry bulb temperature. So we go to 35 and we select that temperature, 35. And then relative humidity. If you see these percentages, 10%, 20%, the curves, these curves, you have 10% here, 20, 30, and so on, right? So that is the curve of relative humidity, okay? So in this case, it's 40%, so we have to choose this condition, right? The 40 line, and we have to intersect it with the 35 Celsius in the bulb temperature, right? In the dry bulb temperature. So is this point that I'm drawing there, right? So that's our point. That's the specific, well, that's the conditions of that air. Okay, so then we have to obtain all the other properties: a specific humidity, enthalpy, wet bulb temperature, dew point temperature, and a specific volume of air. Okay, so the first thing is to obtain the specific humidity, or in this chart it says moisture content, that is over here, and you can see that is the specific humidity because it's in kilograms per kilogram of dry air, right? So if we follow the line from our point to the right side, we're going to reach a value, in this case 0.014, right? So that's our value, 0.014 kilograms of water per kilogram of bone dry air, right? So that's the first point. Then it says the enthalpy. The enthalpy is over here, right? Enthalpy is over here on the left side. And to obtain that that value, we have to follow the lines, the lines, well, that went off from the enthalpy at saturation to that point. So if we try to follow that line, let me use another tool to show it more clearly. If we follow this line, okay, we're going to have a value of, let's see, 71.5, let's say, or 72. Okay, so we write down 72, and then the units, right? In this particular diagram, it's kilojoules per kilogram of dry air. So kilojoules per kilogram of bone dry air. Okay. Any questions for the moment?
I have a doubt, teacher.
Yes.
How accurate the results must be?
Well, for me, as long as you are in the like between the same lines, for example, here if you see it's 71 and it's between 71 and 72, right? The value. So as long as you give me one of that values between 71 and 72, it's fine.
Okay.
Okay, because many of the values are difficult to obtain very precisely, right? Because you have to draw lines and so on. But yeah. Okay, so then the wet bulb temperature, right? The wet bulb temperature is when the air is completely saturated with water, right? Or we can say it like the relative humidity is 100%. Okay, so if we follow the lines of the relative humidity, we're going to have the 50, 60, 70, 80, 90, and the 100 is the last line, right? The saturation line that it's called. And here is, right, wet bulb or saturation temperature. Okay, so we have to follow the line of the enthalpy and go to the saturation line. In this case, this point that I'm drawing here, right? It's bigger than it should, just for you to see it, okay? And then we have to read the temperature in there. If you see the big the separation lines between these 20 and these 25, each line is 1 degree Celsius, right? So the wet bulb temperature would be 20, 21, 22, 23, 23.1, whatever you want to assign there, right? It's almost 24, but it's not exactly. If you want to obtain a better value, what you can do is the following. You put your ruler on the saturation line and the intersection, and then go down vertically to the lower part of the diagram. And there you're going to, is the same temperature. Is that temperature that you find in the saturation line, or if you draw the line to the saturation line and then go down to the dry bulb temperature, is the same temperature, is the wet bulb temperature, right? So here, if you read the value, it should be 23.6,
right?
23.6, I would say, right? 23.6 Celsius. Okay, so that's the wet bulb temperature. Then it's the the dew point temperature. The dew point temperature, remember, that is when we reduce the temperature of that particular air, when we're going to find the first part of the liquid, right? The first drop of liquid. Okay, so to obtain that one, what we can do is from the point of our air, that is 25 Celsius in dry bulb temperature and 40% of relative humidity, we just reduce the temperature, right? So we draw a line. We draw a line from our point, just reducing the temperature, but not changing the amount of water in dry air, right? Because that is not changing. You will have that same amount of water, just that we have it at different temperature. Okay, so when we reach the saturation line, that will be our temperature, right? The dew temperature, the dew point temperature. So if we go down, we're going to obtain the dew point temperature. That will be 19 Celsius, right?
Yes.
19 Celsius. So we have 4 of the data, and we're only missing the specific volume of air. The specific volume of air, you can find it. Wait a second. You can find it in these straight lines that cross the diagram, right? That one is the 80.80. Sorry, what is the units? Oop. Nah, I can find it. The units of this one, this particular diagram. sorry, cubic meters, it's down here, cubic meters per kilogram of dry air, right? So that's telling me that 0.80 cubic meters or whatever you have, right? So if we see our point, a particular point is between the 0.85 line, right? This one that I draw in yellow, and the 0.90 that is over here, right? Those two yellow lines are our point is between those two lines, right? So the specific way, well, the ideal way of doing this is to draw a line that crosses through our point, right? From one line to the other one, from one yellow line to the other one, and to measure how much is from one side and the other, and knowing that the specific volume is going to change 0.05 cubic meters per kilogram of air, right? So I don't have a ruler for my screen, so I'm not going to do it with a ruler, but I'm going to say that it's like the half and half of the half. Let's say that is around 4/5 of the length of it, right? So if it's at 4/5, you would have a specific volume of 0.89, right? Okay, so that's the value that I'm going to write 0.89 cubic meters per kilogram of bone dry air. Okay, and that's it. That's how you read this this chart, right? The psychometric chart. Any questions for how did I obtain any of the data, or what does any of the lines in the diagram means?
Yes, could you repeat how did you get the specific volume of air, please?
The specific volume, if you look at the diagram, I draw two yellow lines, right? That's the two yellow lines means the first one from left to right is that the humid volume is 0.85 cubic meters per kilogram of dry air, right? And the second yellow line is 0.90 cubic meters per kilogram of dry air, right? That is correct?
Yes.
Okay, so then the only thing we have to do is to see how far away from any of the points is our point. Our point is the one in the middle, right? In the middle, here is our point, right? So we have to see how far or how close to the other lines are, right? So the difference between one yellow line and the next one is 0.05 cubic meters per kilogram of dry air. Okay, so if you say that this line is around, 80% of the way from 0.85 to 0.90, well, you multiply that that 0.8%, that 80% for 0.05, and then you add it to the 0.85 line, right? Make sense?
Yes, thank you.
Mm-hmm. Any other questions on how did I obtain any of the values?
Yes, I have a question in one of the dew points. I don't get it too well.
So you start at the your point, right? In this case, 35 degrees of dry bulb temperature and 40% of relative humidity, right? Okay, let me. Maybe it's easier if I. Well, okay. So the whole point is that you know that mass is not going to change because you change temperature, right? The mass of water in the mass of air should be constant, right? You're not changing.
Okay. Yes.
Okay. So you're going to lower the temperature. Okay. You want to know when you lower the temperature at what point that air is going to be saturated, and then at that temperature the system is going to start condensing, right? The water is going to start condensing after that temperature. Okay. So from that point, I'm going to draw a line and a new line with another color, with green this time. With that in mind, we start from our point and reduce the temperature. This is a green line right now, right? So we reduce the temperature until it reaches the saturation line. That is the curved line on the left. You see?
Okay. Yes.
That new green line. Okay. So at that temperature, the system is going to be saturated. So you can dissolve more water on there at that temperature, right? So if that will be the dew point temperature. And to read it, you go down from that point, you go down to the dry bulb temperature, and you can read the temperature there.
Okay.
That at 19 Celsius, this particular system would start condensing, right?
Okay. Yes, I get it now. Thank you.
You're welcome. Okay, so any other question before we change to the next problem? Okay, so this chart is particularly useful, of course, this only works for water and for air, right? Yeah, you can have this type of psychometric charts for any mixture of a condensable vapor in a gas, right? But the usual thing is to have it for air. Okay. The thing that is very interesting about this diagram is that you can obtain many properties. In this case, specific humidity, enthalpy, wet bulb temperature, dew point temperature, and specific volume of air by having two points of data, right? The dry bulb temperature and the relative humidity. So from those seven different variables, as long as you have two, you can obtain all others, right? So it's a very powerful chart, and you can obtain it very quickly. Instead of using the equations, you can obtain any of these data using the equations that we saw on the presentation about multi-phase multi-phase systems, right? But in this chart, you can obtain it quicker than that. So it's very powerful. Okay, so that's that problem, right? So let me change to the next one. Let me erase all those lines. Okay. So now we have a problem of mass balance, right? This problem, as somebody told me on the email, had a thing about the units. It says an air conditioner cools 226 cubic meters per minute, should be, not meters per minute, cubic meters per minute of humid air at 36 Celsius and 98 relative humidity to 10 Celsius, right? So the first thing we need to do is, well, it says to do a degree of freedom analysis to prove that enough information is available to determine the required rate of condensation, right? Okay, so the condenser would be something very simple. We have an inlet, an outlet of humid air, and an outlet of water, right? This is the water that is being condensed, right? So we have 226 cubic meters per minute of humid air that is at 36 Celsius and 98% of relative humidity, right? Relative humidity, okay? And it says an area relative humidity to 10 Celsius, right? So we know that the outlet is 10 Celsius, okay? So that is the information that we have. Okay, so we need to obtain if this problem can be done or not, okay? So, of course, we're going to have a mass, well, this is going to be air, all right? Bone dry air and water. And here we're going to have air, and we're going to have water too, okay? So, if you see these currents, it appears that we don't have too much information about the system, right? We don't know the fractions of water or air in any case, right? And we don't have the mass of water that goes out as condensable or the mass of air or water that goes out from the system, right? But we have a lot of information about the gas that goes in the system, right? So we have 226 cubic meters per minute of humid air that is at 36 and 98% of relative humidity. So with those values, if you do a degrees of freedom, okay, so if you do a degrees of freedom as we are now, without doing anything, degrees of freedom, is the unknown variables, right? Unknown variables will be one from the composition of air and the mass that is getting in, so 2, 1 for the condensable water, 3, 1 for the amount of water on the outlet, and 1 for the mass in these currents, right? So we have 5 unknowns, and we only have 2 components, right? So we have 3 degrees of freedom. So we can't solve that problem unless we do something else, right? And that something else is, well, use the psychometric chart to obtain those values, right? With the 226 cubic meters per minute and the condition 36 degrees and 98% of relative humidity, I'm going to draw those points, right? 36 degrees. Again, it doesn't say if it's drier or wet bulb or dry bulb air temperature, so we have to assume that it's dry bulb. So I'm going to draw the point here, 36 Celsius, right? And then the relative humidity at 98, right? So 98%. So 98%, 98% is not in this chart.
Teacher, in that case, what do we have to do?
In this case, well, the problem is that we can't. Why? This problem is wrong then. Well, at least we can't solve that with this psychometric chart. I'm terrible. Sorry, I put the psychometric chart that wasn't the correct one. Okay, so let me change a value so we can obtain it, right? Sorry for the inconvenience, guys. I put the wrong chart on the homework. So let me change this value to whatever. Let me change this value to 70%. Sorry for that, guys. 70% of relative humidity. Okay, so if we have that point, then we can obtain all the information that we have. Well, the system gives us, right? Sorry, it's this point over here. And let me erase that one. Okay, so so then we can, for example, using that particular point that we have there, we can obtain the specific volume of air, right? And the specific volume of air, remember that you have to read it using the diagonal lines. For example, here we have the value between 0.90 and 0.95. That would be the next. Let me draw that line. The 0.95, that would be this line, right? So we have our air between these two lines, right? The 0.90 and 0.95. Okay, so we have to choose how far or how close from each one it is. So I'm going to say that here is the meal. So let's say that it's at 25% of it. Again, the separation is 0.05. So if we do 0.05 times 0.25, we reach at 0.021 and we add 0.90. So I'm going to say that the specific volume is 0.9125. 0.9125 cubic meters per kilogram of bone dry air. Okay. Any questions on how do I get that value?
No.
Okay. So with this value, we can obtain, with the specific volume, we can obtain the amount of bone dry air, right? Because you have it here. You have cubic meters per kilogram of bone dry air, right? But let us obtain all the other conditions, all the other variables, and then we will use them. Okay. So again, if we start at the point and we go to the right, we're going to find the specific humidity. And that specific humidity in this case is 0.0268. So let me write it down. The specific humidity, or omega, it's equal to 0.0278 kilograms of water per kilogram of bone dry air, right? And then we can obtain the dew point, right? The dew point temperature. And again, if we go to, let me change. We go to saturation line. Sorry, that wasn't. We go to the saturation line, and then from that saturation line to downwards, we are going to obtain that this is around 29.7. So the dew point temperature is equal to 29.7 Celsius, and we can obtain, of course, to the wet bulb temperature in orange. So we go from this point to the line, and then from that line downwards, and we obtain that is 30.9. 30.9 Celsius. Okay. So now we have enough information to do this, to obtain the data on the inlet of it, right? We have with the specific volume, we can obtain the amount of air that we have, and with the bone dry air, and with the omega, or the specific humidity, we can obtain how much water, or the fraction of water, is in that air. Okay, so let me do that part. Okay, so to obtain the amount of the kilograms of bone dry air, what we do is that we do a relation, right? We know that we have 226 cubic meters per minute, right, of this particular air, and we know that we have I'm confusing data. And we know that each cubic meter has one, for each 0.9125 cubic meters, we have 1 kilogram of bone dry air, right? That's the information that we have because of the specific volume, right? So if we do that calculation, we obtain 247.67 kilograms of bone dry air. Everybody agrees? Okay, or any question about it?
Now it's clear.
Okay, so now we have the amount of bone dry air, right? We have one of the components in the inlet. And then with the specific humidity, we can obtain the amount of water, because now we have the amount of kilograms of bone dry air, right, that we have in the system. Sorry, this is per minute, right? Okay, so with this 247.67 kilograms of bone dry air per minute, we know that we have 0.0278 kilograms of water per kilogram of bone dry air, right? So we cross the units on this. This is the mass of H2O in the inlet, right? This would be, let me do the multiplication. 6.88 kilograms of water per minute. Okay. So now we can obtain, of course, the fractions of each of the components, right, of air and of water. I'm going to do two methods to obtain it so you can see the difference, right? So the first one would be that the fraction of water in the first current would be the 6.88 kilograms of water that we have, right, divided by the total mass, that is the 247.67 of bone dry air plus 6.88 of water, right? So this one, let me do the so that gives you 0.027. 0.0027. And of course, the fraction of bone dry air in the current one would be 1 minus that one, right? So 0.973. Okay, so that's one way of doing it. The other way of doing it is just using the specific humidity. If we know that specific humidity is telling us that we have 0.0278 kilograms of water per kilogram of bone dry air, right? So if we do like a base of calculus of 1 kilogram of bone dry air, we're going to obtain the same thing, right? The water in the stream 1 would be that we have 0.0278 kilograms of water in 1 kilogram of bone dry air plus the 0.0278 kilograms of water, right? And this, of course, should be the same data, that is 0.027. That makes that the bone dry air is equal to 0.973. Okay. The difference between doing any of those is, well, that you can obtain quicker the molar fraction of water, right, using just this equation instead of obtaining the mass and changing and so on, right? But any of the two methods is fine, right? Okay, so now we have about yep.
Teacher, in the WH2O, what did you multiply the 0.027?
In what part, sorry?
In the WH2O.
Ah, yes. Okay. For the first one or the second one?
The first one.
The first one is just the mass of water that I obtained here, divided by the total mass of that stream, that is the bone dry air.
Yes.
Right? Because we have two components.
Yep. But in the bottom one, what is WBDA times 0.027?
I don't see that value.
0.027?
Also the second one, this one?
Yes. What is the value of W?
Okay, the value of W is the fraction of water, right? The mass fraction of water in stream 1. So I'm obtaining it through two different methods. One is obtaining the mass of water and the mass of bone dry air and doing the operation, that is this one, the first method, right? And the second method, this two, is to obtain it through the specific humidity that is over here on the line, right?
Okay.
Okay, so there is only two different methods to obtain the same thing, to obtain the mass fraction of water. Yep.
Okay. Thank you.
So I think I'm going to need a new page. Okay, so with this we have all the information about the stream 1, right? So if you follow the degrees of freedom, now that we have those two numbers, that is the mass of it, because we can obtain it through addition of 247.66 kilograms of bone dry air plus 6.88 kilograms of water. We are subtracting two variables, and now we're left with one degree of freedom, right? But we can erase that degree of freedom, of course. What I'm going to do, let me clear all these things. Okay, so we reach again at our point, right? But now we want to see if we can obtain the properties of the air that is getting out of the system after the condensation happened. Okay, so in this case, you have to understand the process first. What is going on is that air that has a lot of water in relative humidity goes into a condenser, and in that condenser, temperature is dropped to 10 Celsius, right? The pressure, the atmospheric pressure doesn't change, and the amount of air doesn't change either. Okay, that bone dry air, it's only getting out from in the condensed current. Okay, so that bone dry air that we calculated already is the same at the outlet. But what we want to see is at what conditions do we arrive of temperature and pressure, of temperature and moisture content and so on to obtain a molar fraction of water. So what we're going to do is that we're going to follow the path of the problem, okay? So we start at our point, that is 36 Celsius and 70% of relative humidity, and then we're going to cool it down, right? But we can't cool it down until any value that we want, right? Because when we cool it down, at some point we're going to reach the saturation line, right? And at that saturation line, the system is going to start condensing, right? So if that happens, the system is going to follow the saturation line because, well, you have a saturated system, and it's going to start following. It's going to start following the saturation line, that is this curved line over here. Sorry for the precision. So it's going to be saturated until it's going to go to the saturation line until we reach the 10 Celsius mark, because that's the outlet, the temperature in the outlet, right? Those 10 degrees. And we know that this system must be completely saturated because we are dropping the temperature a lot, right? So this is our new point. This over here, down here at 10 degrees, and 10 degrees and at the saturation line, that's our outlet in this case, right? We follow the saturation line. So in that point, of course, we can obtain the specific humidity. So I'm going to say the specific humidity at the outlet, right? At the outlet, it's 0.7, 0.007, 0.0076. Okay, so omega in the outlet, that is the third one, is going to be 0.0078 kilograms of water per kilogram of bone dry air, right? And again, as we did in the second way of obtaining the molar fraction, the mass fraction of water in the extreme one, we can do the same thing. The mass fraction of water in current 3, it's 0.0078 kilograms of water divided by 1 plus 0.0078 kilograms, right? And if we do that calculation, we obtain a molar fraction of 0.0077. 0.0077. Okay. Any questions on why did I obtain that value, or how did I obtain it, or how did the process went from the inlet to the outlet? Okay. So if we have this new value, if we have this value for the molar mass fraction of water, then we reduced another degree of freedom, right? -1, and that of course is 0 degrees of freedom. And now we can solve this problem, right? We have enough information to solve it. Okay, and to solve it, well, is the more or less the same way that you have done it. Okay, so let me write these values. Let me write these values in the other page, so we can have them. Okay, so we have our condenser, we have our inlet, our outlet, and we have here M2, that is just water. We have here air, we have here water, and that particular value, the molar fraction of water in stream 3 is 0.0077. And of course, the molar fraction of bone dry air would be the subtraction of that. So 1 minus 0.0077, 0.9923, right? 0.9923. And we have the values for the first part too. That is, well, for the inlet. That is that the fraction is 0.027 of water. 0.027 of water. This is water in stream 1. And air, bone dry air in stream 1 is equal to the subtraction of that. That is 0.973. Okay. And we have the last part of our system, M1 and M2. M1, of course, we can obtain it. Let's just do the addition. The M1 is going to be the 247.66 plus 6.88 of water, 254.55. 254.55 kilograms per minute. Okay. And we can obtain M3 doing a calculation too, because we know that the molar fraction of bone dry air in 1 times M1 has to be equal to the bone dry air in the third one times M3, right? So we know the value of all this, so we can obtain M3 as the mass of water, well, the mass fraction of water of a bone dry air times the mass of the current divided by the mass fraction of bone dry air in stream 3, right? And we have all that data, of course. So we have that this is 0.973 times 254.55 divided by 0.9923. Let me do that calculation very quickly. This gives us 249.59. 249.59 kilograms per minute, right? So now we have M1, M2, and we're only missing M2. Sorry, M1 and M3. So the only thing we're missing is M2. Of course, if we use the global balance, M1 should be equal to M2 plus M3. So M2 is equal to M1 minus M3. And we substitute the values, right, to obtain the amount of water that was condensed. So M1, we said that it was 254.55 kilograms per minute. And M3 is 249.59 kilograms per minute. And that gives us that M2 is equal to 254.55 minus 249.59, 4.96 4.96 kilograms of water per minute. Okay, so that solves the problem, right? That was the value that we wanted to obtain, of course. Right? So, any questions on how did I arrive at those values?
Why is M3 equal doubly that division?
It's just this is okay. Sorry, this is the bone dry air balance, right? So this equation over here, the one with the arrow, is the bone dry air balance, right? Is the mass of bone dry air in the inlet, so in one, should be equal to the mass in the outlet, right? To calculate those masses, you have the mass fraction of bone dry air in stream one times the mass of that stream, and that should be equal to the mass fraction of bone dry air in the outlet times the mass on that outlet, right?
Thank you.
Welcome. Any other questions, guys?
Yo tengo una pregunta. No es la única forma de resolverlo, ¿verdad?
No.
Porque, o sea, yo no cambié ¿cómo se llama? La humedad relativa. O sea, seguí usando el 98%.
Ajá.
No sabía que se tenía que usar la carta psicométrica.
Ok, claro. O sea, sí, es que era que lo resolvieran con la carta psicométrica, porque de eso se trataba la actividad. Pero sí, claro, se puede resolver a partir de usar las ecuaciones que vimos.
Ajá.
Sí, sí se puede resolver también con eso.
Ok, gracias.
Okay, and there is a quicker way of doing this. Okay, so this was the long way for saying something. I'm not going to show you the quicker way or the fast way. Okay, so the two values that I'm going to need is the specific humidity at the inlet and the outlet. Okay, so let me copy those. Is omega 1 is equal to 0.0278. So omega 1 is equal to 0.0278 kilograms of water divided by kilogram of bone dry air. And omega 2 is equal to 0.0078. 0.0078 kilograms of water divided by kilogram of bone dry air, right? And we know that we have the amount of bone dry air is 247.67. 247.67 kilograms of bone dry air per minute. Okay, so if you pay attention to these two values, the two omegas, the two specific humidities, they're telling you that it's per kilogram of bone dry air, right? That value is not going to change at all in the inlet and the outlet. We need to do conservation of mass, and if we're only condensing water, the bone dry air should stay the same, right? So what we can do is that these two values are telling us the difference in amount of water in the inlet and the outlet. So we can do a delta omega. That delta omega is the difference between one and the other. Okay, so in this case, 0.0278 minus 0.0078. That gives us 0.027 minus 0.0078. That gives us 0.02. 0.02 kilograms of water per kilogram of bone dry air. Okay, so this is telling us the amount of water that's going to be exchanged between the inlet and the outlet, and that water, of course, is going to go to the condense in the M2, right? Okay, so if we know the amount of kilograms of bone dry air, we can obtain the mass of water in stream 2 as the difference, that is this delta, this delta omega, times the mass of bone dry air. Okay, so in this case, 0.02 kilograms of water divided by kilogram of bone dry air times the mass of bone dry air, that is 247.67 kilograms of bone dry air per minute, right? So we cross the units and we obtain that the water using this method is 247.67 times 0.02, and that gives us 4.9534. 4.9534 kilograms of water per minute. Okay, so if you see these two values, of course, they are a little bit different, just a tiny little smidge, because we used different decimals in the long process. We didn't use all the decimals, right? So this was the value for the long method, and this value is using the short method. Okay, so of course it's easier to do it with the short method, right? And I encourage you to use that one because it's a lot quicker, and it's why every property in that psychometric chart is in kilograms of bone dry air, right? That's why we use it in per kilogram of bone dry air, because it's very easy to obtain the masses and so on. Do you have any questions on how did I arrive to the mass of water using the short method or the long method for that matter?
I have a question.
Yeah.
Why do we have to have a delta omega?
Because, well, that change in the specific from the inlet to the is the water that was transferred to the condenser, right? You had an air that has a high humidity, 0.0278 kilograms of water per kilogram of bone dry air, and you condense a lot of water on that air, reached a value of a specific humidity of 0.0078 kilograms of water per kilogram of bone dry air. So the difference between those two numbers is the water that was condensed. So that's why I use that delta. You
Okay.
You are a little bit different operation, but it's the same thing.
Okay, thank you.
So, again, well, so that 0.02 kilograms of water per kilogram of bone dry air as the delta, it's the water that was exchanged in the process, right? And that exchange, of course, went to the stream of water, condensed water. Any other questions, guys? Okay. So then let me go to the final problem. That is the hardest one, of course. So it says wet solids. We don't know what kind of solid, but it's wet solid, right? Pass through a continuous dryer. Hot dryer enters the dryer at a rate of 400 kilograms per minute and picks up the water that evaporates from the solids. Humid air leaves the dryer at 50 Celsius, containing 2.44 percentage of weight of water vapor, and passes through a condenser in which it's cooled down to 10 Celsius. The pressure is constant 1 atmosphere through the system. Okay, so then we have a couple of questions. At what rate kilograms per minute is water evaporating in the dryer? B, use the psychometric chart to estimate the wet bulb temperature, the relative humidity, the dew point, and specific enthalpy of the air leaving the dryer. And use the specific chart to estimate the absolute humidity and specific enthalpy of the air leaving the condenser. And the last one, use results of part B and C to calculate the rate of condensation of water. Okay? So the first thing to do, of course, is to know what kind of process do we have here, right? So the first thing is that we have a continuous dryer, right? A continuous dryer. So we're going to draw a continuous dryer. And it says that air enters, blah, blah. Okay, so we're going to have an inlet. If you remember one of the first, well, you should have seen the different kind of operation units with Hugo. or I don't remember if you said it with me, but in a continuous dryer, what you have with an air continuous dryer is that you have inlet and outlet of the solid. In this case, we have solid in the inlet and water, and we have solid in the outlet and water. Okay, and we have a stream of air. This is air, bone dry air, and water, of course. And here again we have bone dry air and water. And I make the let me change this because if not I'm not going to have space to write down the things I need. Okay, so to insert here, we're going to put the solid and water. I'm not just changing the way of doing it. And here I'm going to have the inlet of bone dry air and water. And here I'm going to have bone dry air and water. And this stream is going to go to a condenser. So here again, we're going to have bone dry air and water. And we're going to have an outlet of just pure water. Okay, so this is the dryer. And this is the condenser. Okay, so the process is that we put solids in one with water that go out in two with less water. We are drying it up. We have air that goes with low humidity in 3 and goes out with high humidity in 4. And then that air in 4 goes to a condenser where some water is condensed in 5. And we obtain, again, drier air or air with less water in 6. Okay, so we have a couple of conditions, right? And so it says that the hot air goes into the dryer at 400 kilograms per minute, right? That's the mass of 3, and pick up the water that evaporates from the solid. Okay, so humid air leaves the dryer at 50 Celsius and a weight percentage of 2.44 weight percentage, right? And passes through a condenser where the temperature is dropped to 10 Celsius, right? So that one. So in this particular process, it seems like you need to well, let me explain first the psychometric part, and I will let you know. Okay, so we have water air that is going to have 50 Celsius and 2.44% in weight of water, right? So we want to trace the system. So the 50 Celsius, well, we have it here, 50 Celsius in the psychometric chart, in blue, 50 Celsius. But what other point do we have in that particular diagram? We don't have any at this particular time, right? Because the value that we have of percentage of water is in weight percentage, right? So this is the amount of water in the total mass of air, right? So we have to convert that. So how can we convert that value to a specific humidity or to a relative humidity? Yeah. We can start with the definition of the molar fraction of water, right? The molar fraction of water is the mass of water divided by the mass of bone dry air plus the mass of water, right? That's the definition of mass fraction. Okay, so you have that. The mass fraction is 0.0244, right? That this value, we have it. Okay, and then we can do an assumption, right? We can say we can obtain the mass of bone dry air using this equation. We have that the fraction is 0.0244, right? And that would be equal to a mass of water that we can assign. So we can say a base of calculus of 1 kilogram of water, if you want to, or any other thing that you want. So this will be equal to 1 kilogram without the letters divided by the mass of bone dry air times that one, right? That mass of the water. So we can solve this equation, of course, right? Okay, so how do I solve it? Well, we can multiply 0.0244 times the mass of bone dry air plus 1 is equal to 1, right? And then we obtain that 1 minus 0.0244 divided by 0.0244 is equal to the mass of bone dry air. If we do that, we obtain that 1 minus 0.00244, sorry, 244.
Why you substitute mass of water by 1?
Wait, let me write down something and I will let you know. 39.8. Sorry, again?
Why you substitute mass of water by 1?
I assume a base of calculus.
Oh, okay.
Just to be able to obtain the specific humidity.
Okay, thank you.
Okay. So now we have the kilograms of bone dry air and the kilograms of water, right? Because we assume 1 kilogram. So omega in that case would be the amount of water that we said it was 1 kilogram of water divided by the 39.98 kilograms of bone dry air, right? So this divided by 39.98 gives you 0.025. 0.025. So this is the specific humidity of that air that is leaving the dryer. Everybody agrees? So we have this value over here, and that value, of course, we can find it on the psychometric chart. We have the 50 Celsius, and now we have the specific humidity that is 0.025. So we go to the 0.025, right? And we see where those two lines meet. So let me draw a line. So we start at 50 and we go up, okay, the whole way. And then we start at 0.025 and we cross it, right? So our point will be the intersection of those two. So the blue dot over here, right? That would be the conditions at which we have the air in the dryer. Well, after the dryer, right? And again, we're going to do a process similar to the one that we did for the previous problem. We have to obtain the conditions at the exit. So again, we need to draw a line. From that point, reducing the temperature until the saturation point. Well, we do that line. To the saturation line, and then follow that line. Follow this line. I'm not very good at drawing. Follow this line until we reach the 10 Celsius line, right? And at that 10 Celsius line, we can obtain again the specific humidity for the outlet of that process, and in this case would be 0.0078, like in the previous example, where we reached to a we reached to the saturation line at 10 Celsius, right? So this is omega in 4, and omega in 6 would be 0.0078 kilograms of water per kilogram of bone dry air. Okay. And that's, well, that's most of the conditions that we need, right? In step B, they're telling us to obtain all the values for the first point, right? For the air in 4. I'm going to draw a point here. Okay, so that's the point in 4. So we obtain the specific humidity, right? That is in 4. We can obtain, of course, here we can obtain the dew point temperature by following the line, the blue line from the point 4 to the saturation line, and then going down. Going down to the temperature, right? So let's say that is 27, 28, 28.5. Let's say it is. Okay, so let me write that down. So the temperature of the dew point in 4 is equal to 28. Yes, 28.5 Celsius. It says that we have to estimate the wet bulb temperature too. So wet bulb in 4. Remember that from the point that we have, we need to follow parallel line. From the point 4, we follow a parallel line to the saturation line, and then we can go down from there to obtain the temperature, the wet bulb temperature, that in this case would be 33 Celsius. 33 Celsius. And another thing, the point we already crossed it. Relative humidity. Relative humidity. We have to pay attention to the lines of humidity. That is, let me draw with orange. So we are between the line of 30% and 40%. I draw them in yellow, right? And I think we are around 20% from the 30 line, so that would be 30. Yeah, like 30%. 33% of relative humidity. The dew point, specific heat, specific enthalpy. Sorry, we can follow the purple line that I draw until we reach to the enthalpy line, and that enthalpy line would be 115, 16, 17. Let's say that specific enthalpy is 117 kilojoules per kilogram of bone dry air. And that's it, right? Yeah, a specific enthalpy of air leaving. Okay, so to solve the C part, we did already. Use to estimate the absolute humidity. That we said that it was 0.0078. A specific enthalpy leaving the condenser. Okay, so we have that part now, right? We have the weight percentage of solids and so on, and then we have to solve the dryer first, right? So it says wet solid passes through a continuous dryer. Hot air enters the dryer at a rate of 400 kilograms per minute and pickups dry air. So this was bone dry air, right? Bone dry air. So we know that this bone dry air that goes inside of the dryer should be equal to the bone dry air that leaves the dryer in 4. and that should be equal to the bone dryer that goes in 6, right? So let me solve the last part, the D point, using these two values, right? So we're going to do the same thing as we did in the previous example. Mass 5 of water is going to be equal to the change in a specific humidity. In this case, is going to be 0.025 minus 0.0078, right? That's the delta, times the mass of bone dry air. That doesn't change at all in any stream. So M5 is equal to the difference that, let me calculate it. The difference that is 0.25 minus 0.178. So 0.072, 0.072 times the mass of bone dry air, that is 400 kilograms of bone dry air per minute. Okay. So this M5 then gives us that the amount of water leaving condensing is 6.88 kilograms of water. Kilograms of water per minute. Okay. Do you have any questions for point B, C, and D?
Yo tengo una pregunta. Lo que va a salir... No, ajá. Lo que va a salir en los condensadores siempre va a ser la diferencia, ¿no? El delta omega.
Ajá.
Y
Sí.
otra, el bulb wet water, no. Bueno, sí, ese solo cambio cuando cambia la temperatura.
¿Cuál?
Ay, es que se me fue su nombre.
Wet bulb temperature.
Wet bulb temperature. Ajá.
Sí, o sea, ese es del punto donde estabas, ¿no? Del punto inicial. Te vas hacia la saturación, que es reduciendo solo temperatura. Entonces, a través de la línea azul que pinté, cuando llegas a esa curva de saturación, ahí mides la temperatura. Entonces, bajas una línea recta, que en este caso está en rosa, hasta la temperatura. Y esa es la temperatura del bulbo, perdón.
Ajá, o sea, pero lo que yo me refería es que esa va a cambiar solo si la temperatura cambia. Por eso en el problema pasado pudo hacer esa relación, ¿no?
Sí.
Ok. Sí. Ya, sí.
Profe, yo no entendí de dónde salió el 33%.
¿33%?
Ajá, cuando sacó... pues sí.
A ver, selecciono un pincel más grueso para que se vea más. Las curvas de humedad relativa son de acá, ¿no? Esta que estoy pintando en amarillo, ¿la ves?
Sí.
Ok, esas son las de humedad relativa, ¿cierto?
Sí.
Entonces, si te fijas, nuestro punto, el punto azul que está aquí, 4, está entre la curva de 30% y 40%, ¿cierto?
Sí.
Entonces, digo, yo a ojo de buen cubero, pues dije que está en el 33%.
Ok.
¿Sí? O sea,
sí, profe. Gracias.
Vale. Okay. So the last part, of course, is to obtain the point A that was pretty easy to obtain, right? It says wet solid passes through a continuous dryer, hot air, because the dryer at a rate of blah blah blah, right? And pick up the water. So here you have to assume, the only thing that you can assume is that you don't have water on the beginning of it, right? Because it says hot dry air, right? So that we can call that water in the inlet of stream. Okay? So it says that it's only going dry air, right? So there are a couple of ways of doing it. One way of doing it is to obtain stream 4 and then using the mass fraction that we have of 2.44% that we have on the problem. That's one way of doing it. And the other way of doing it is through the specific specific humidity in the stream 4, right? That is 0.025 kilograms of water per kilogram of dryer, right? So the mass of water in stream 4 is going to be equal to the specific humidity, so 0.025 times the amount of bone dryer, that is 400 kilograms, right? So the mass in 4 of water, or the mass that was evaporated in the dryer, is 400 times 0.25, right? So that gives you 10 kilograms of water. Okay, and that's it. This is the result for A. This is the result. Is the result for D. This is the result for C, and all of this is the result for B. Okay, so do you have any questions on how to solve these problems? Okay, so well, we have 3 minutes of class, so I'm going to start the new topic, that is transition mass balances. So I will see you on Monday at 8:30 as always, and that's it for today. Have a good weekend, guys.
Thank you, teacher.
Thank you, teacher.
Thank you, teacher.
Sí.
Later.
Yo tengo una duda, pero sobre el proyecto, o sea, la entrega del proyecto de hoy.
Ajá.
O sea, es que como que todo nuestro proceso es muy grande, entonces tenemos que, o sea, ya llevamos como una parte de lo que es el balance de materia, pero no sé si tenemos que hacerlo ya todo, o sea, todo, o está bien.
Pues habíamos quedado en algunas reglas, ¿no? Que para la selección del proceso. Entonces, abro ese documento, permítame un minuto, y te digo. Entonces, habíamos quedado que tenía que tener 10 operaciones unitarias y un reactor, ¿no? Entonces, sí, aunque tu proceso tenga, yo qué sé, 50 operaciones unitarias y 10 reactores, mientras hagas el balance de una sección que tenga 10 operaciones unitarias y un reactor, está bien.
Va. Vale. Sí.
Va.
Gracias.
De nada.
Bye.
Chao. ¿Alguna otra duda, chicos?
Teacher, can we upload, podemos subir la tarea con las mejoras para obtener una mejor calificación?
Sí, o sea, exacto. Sí.
O sea, esta que acabamos de resolver, pues.
Bueno, la calificación igual les puse, o sea, si la habían entregado la tarea, les había puesto 100.
Ok.
Pero sí,
bueno.
o sea, igual los problemas que están ahí, pues tómenlos en consideración porque problemas de ese estilo pueden venir, ¿no? O sea, bueno, son del tipo de cosas que tienen que saber.
Ok.
¿Sí?
Vale, gracias.
De nada. Bueno, entonces nos vemos, chicos.
Ya espero hasta el lunes.
Hasta luego.
Gracias.
De nada, bye.
Bye.
Chao, bueno, chao.